a fifth-year PhD student at Stanford University, and it's my honor to give the talk here. So today I will be talking about my recent works, and the major purpose of this talk is to have some more to give people inspirations on this exciting field of quantum machine learning, and also trying to find the applications of quantum cross entropy in various disciplines, from high energy theory to condensed matter. And hopefully we could have some new ideas emerging by having this talk. So first, let me talk a bit about the motivation of this project. So as physicists, we all want to answer the ultimate question, basically to understand our universe better. And sorry, could anyone like mute their sound so that there wouldn't be this keyboard sound? Yeah, awesome, thank you. Yeah, feel free to interrupt me if there are any questions. I'm happy to answer them either in Chinese or in English. Thank you. So there are many aspects in understanding our universe. So for gravity people, they would like to know more about the de Sitter quantum gravity. And if that's too hard, then they will say, oh, black holes also have horizons. Then maybe we should understand black holes first. And for condensed matter theorists, they will say, well, high temperature superconductors are very interesting. Or maybe we want to understand strange metals better. So there are many aspects of understanding our universe. However, all these problems are very hard, and we definitely don't want to like spend our lifetime like try here and there. So we might wonder if there are some other approach that we can tackle all these problems in a more unified way. And my approach would be, why don't we try to model a quantum system on a quantum computer using quantum machine learning, so that these techniques can help us understand all these questions automatically. And once we solve one of the questions, the other can also be solved by machines in a easy and automatic fashion. So that's basically the motivation, and it might be a long shot that we probably need to wait 100 years to see all these coming to truth. But why not trying? So here comes the outline of this talk. First, I will be talking about some basics of machine learning, and then I will be talking about a central concept in machine learning, which is the classical cross entropy. And then I will be talking about the term that we defined in our earlier paper, which is a quantum cross entropy, and of course its physical meanings and various properties. And then we will talk about maximum likelihood principle, which is a central idea in machine learning that is used to design many machine learning algorithms. And then we will proceed to talk about the relation between cross entropy and the likelihood. And then we will conclude the talk by looking at the outlook and see what kind of future work can be built upon. So the talk is mainly based on the work that was done by me and my collaborator Yishu Wang, who is also a Fudan alumni, and also my work in June. And there are also ongoing and future work, and I will be happy to talk about that. So let's start from a crash course of machine learning. So first, let's talk about different types of machine learning. So one easy way is to do supervised learning, where we have our input data and output variable, and we want to use an algorithm to learn the mapping function from the input to the output. One example would be the housing prices. We all know that in different regions, we will have different housing prices, and house price can be affected by different factors. And these different factors can be considered as a vector, or we say the input variable X. It can be how large the house is, which region it is, what the crime rate of that region, and how good the school it is inside the region. And the output variable Y will be the price. So it is a very common problem that can be easily solved by ways like regression. And now we also have another type of question, which we call it the unsupervised learning. Here we only have some input data X and no corresponding output variables. And the challenge now is to model the underlying structure or distribution in the data. One example would be the clustering method, which means we might have a massive different groups of data, and then we want to classify, well, these data might be related, and those data can be made in another group. And there are also other more advanced machine learning methods or categories. For example, semi-supervised learning is kind of a combination of supervised and unsupervised learning. And we also have reinforcement learning, meta learning, transfer learning, etc. And how do we usually do machine learning? Here is a recipe that I built based on my own experiences, and other people might have some modified version. So basically, we start with having a training set. And with this training set, we will need to design some learning algorithm to try to learn the data and find some underlying structures or some rules so that we can make a rather generic prediction function. So when the new data come in, which we call the test set, we can use this prediction function to easily generate our prediction. So that's basically the main idea. So any questions up to this point, like on the motivations and details? So if not, I'm going to move on. So we finished a very short crash course on machine learning. Now we are going to talk about this central quantity, which is a classical cross entropy. So this quantity is used across many different types of learning algorithms. Usually it's considered as a cost function. So what we do is to tune the parameters so that the classical cross entropy can be minimized. The definition is that for discrete probability distributions P and Q with the same support, the classical cross entropy can be defined as follows. And of course, just like any other quantities, there are different ways to understand it. From a purely information theoretical perspective, we can consider Px as the true distribution and Qx as the perceived wrong distribution. And this quantity can somehow tell us how different these two distributions are. And also from the machine learning perspective, we can consider Px as a distribution comes from data. And Qx is based on model parameters. And when we talk about model parameters, that's the parameters represent our model. And when we tune the model parameters, we expect to enhance the performance of our model. And when the model parameters are optimized, we can call we have successfully finished our machine learning procedures. As a simple example of using classical cross entropy, we can talk about the binary classification problem. What is a binary classification problem? We can have a data set which contains a lot of data points, xi's and yi's. Xi can be a vector which represents features, and yi can only take on two values, 0 and 1. One simple example can be, while many professors and students receive many emails daily, some are spam emails that are useless and should be going to the trash, and some are useful emails that worth reading. So this yi can represent whether this email is a spam or not. If it's a spam, it's 1. If it's not a spam, it's 0. And xi can be a vector that represents the features of this email, say whether it contains on sale, this word, or how long the email is, how many pictures this email has, how many attachments this email has. All these can be considered as features, but we can only have two outputs. Either it's a spam or it is not. So how do we model this? So we can do logistic regression to help fit the data so that we can find the optimal model parameter to tell us, to say, basically say, well, if this email has more than 10 pictures, it's very likely to be a spam. So how do we actually do this? So we need to use this curve, which is the graph of the sigmoid function, and we are going to be using this function. So the learning algorithm is actually very simple. Our goal is to minimize the classical cross entropy, and usually we have simple methods like gradient descent. And as we've written down here, this h theta is a classical cross entropy, and it exactly matches with the form we had earlier in the definition. So this is just to give you some idea of what classical cross entropy can do. So don't be worried if the details are kind of hard for you to grab at once. So now we are going to talk a bit more about what it means to have classical cross entropy in the information theoretical perspective. So here we are going to talk about the relation between classical cross entropy and data compression as a warm-up of our new results on the relation between quantum cross entropy and data compression. So as usual, the definition of classical cross entropy is here, and we want to say this is actually the compression rate when we have a suboptimal compression protocol. So first, of course, I have to introduce a bit on what data compression really means. So let's say we have two Mars creatures, Ada and Bob. They communicate, of course, use their Mars language, which contains only 4 letters, C, D, E, and F. And in reality, an average Mars creature talks in a way that C, D, E, F occurs equally likely, as shown in the chart. However, Ada has her own unique way of speaking, so that she uses C much more often than using D, and E and F are the least likely to be used. So now the idea is when Ada is sending her message to Bob, we want to encode C, D, E, and F using bits 0 and 1 to represent the message. And our goal is to use as few bits as possible. So smart as you probably will say, well, it's easy. All I need to do is to encode those letters that are more likely to happen using shorter bit strings. And for those letters that are less likely to happen, I will be using longer strings. And that by doing that, we could see that if I encode all the messages based on an average Mars creature, then I can just represent C using 0, 0, D using 0, 1, E using 1, 0, and F using 1, 1. On the other hand, for eta, the optimal way is, of course, to represent C using only 0, because doing so this way can reduce the expectation value of a certain sentence that eta says. And for D, we can encode it using 1, 0. And for E and F, because they are less likely to happen, I can just safely encode them using longer bit strings. And that is an optimal way for Ada's unique speech patterns. And here we could see that when we do this in the optimal way, which is design a protocol specifically for Ada, then the encoding is optimal and the compression rate is 1.75, which means for each letter Ada says, on average, we need 1.75 bit string length of bit strings to represent it. However, if in reality we are really having an encoding decoding system to send message from Ada to Bob, it's very expensive to design a protocol specifically for Ada, because other Mars creatures like Sienna, Elena, and David probably also will be using the same encoding decoding system, and it's much more efficient if we just use the universal encoding way, which is based on QX, and which is suboptimal for Ada. And when this is the case, the compression rate is the classical cross entropy, and it's 2. It's a little bit larger when it's designed specifically around Ada. So here, classical cross entropy tells us that if we are using a universal protocol that is suboptimal for the true data distribution Px, we can using classical cross entropy to determine the compression rate. And in this case, under this protocol, the compression is still successful and faithful. So now that we have had some understanding of classical cross entropy, we jump into the quantity that we defined earlier in February, which is a quantum cross entropy. So as we all know, in the classical case, we deal with the probability distributions. So in the quantum case, we deal with its sisters, which is a density matrix. So the quantum cross entropy is defined as follows, and we can still view it from different perspectives. From the information theoretical perspective, we can consider rho as a true value and sigma as a perceived wrong value. And from the machine learning perspective, we can say, well, rho comes from real data, and sigma is a model parameter, the model parameter that we are going to tune and help improve our learning algorithm. Of course, when we define a new quantity, we would like to talk about its properties. So we have proved in the paper that it has positivity, and it's invariant under unitaries. It's linear on the first argument, and it has convexity on the second argument. It is also joint convex, and it has a lower bound, and here F rho sigma is the fidelity. And of course, we would like to know more about this quantity, especially since we have had some understanding of this quantity in the context of quantum information, more specifically in quantum data compression. It would be nice to know what this quantity stands in condensed matter systems, for example, many-body systems, when we have time evolutions, or if it has some gravitational meanings, before jumping into these open questions, let's first have more understanding on how quantum cross-entropy is related to data compression.
Can I ask a quick question?
Sure.
The quantum cross-entropy, isn't it related to the relative entropy?
Yes, it is. Yes, it is. It's like, so for relative entropy, we have trace rho log rho minus trace rho log sigma.
Uh-huh.
And this, yeah, and this quantum cross entropy is basically the second term as it. So just like its classical counterpart, in the classical case, we also have classical relative entropy, which is also called as the KL divergence. And the cross entropy is also the second term of that classical relative entropy. So in the past, people have focused a lot on classical relative entropy, just as people have done a lot of research on quantum relative entropy. Recently, the emergence and the popularity of classical machine learning has shown people that classical cross entropy has its unique applications, and usually in the context of machine learning, classical cross entropy is more widely used than the classical relative entropy. And there are some cases that classical cross entropy has its own well-defined meaning, but the relative entropy cannot be well-defined. So basically, the development of machine learning has made classical cross-entropy separately important from classical relative entropy. So what I would like to see is to see quantum cross-entropy rise and have a similar status, since quantum machine learning is emerging. So that's why people have talked a lot about quantum relative entropy, but rarely paid attention or even bothered to give a name to quantum cross entropy, despite this term appear here and there in references in the middle of calculations. And I think this quantity is worth noting. So we give it a name and try to look at its properties. And here I'm presenting a operational perspective of what it means, but it's only in the context of data compression. And my hope would be to find its other meanings, either in the context of quantum information theory or in quantum gravity.
I see. Thank you.
So here, again, just like in classical data compression, we assume that Ada's own unique quantum information source is rho zero, but an average Mars creature emits sigma zero. And in my work, we construct a protocol that is optimal for source sigma zero and can also do lossless quantum coding for rho zero. So this protocol is quite universal. And unlike many protocols that are very popular in the references, those protocols require a perfect knowledge of source. And if you're a little bit off on the information of the original source, your compression will just fail. But here, this protocol is much more tolerant that if you're doing some suboptimal thing, your compression will still be perfect. And a complete proof is presented in paper, and I will show an outline of the proof later. So in this case, our conclusion is that the compression is just the quantum cross entropy, which is exactly the same case as the classical case. So let's talk a bit about the setup. So the setup is that we can both decompose the sigma zero and rho zero in their eigenbases. And as we know that because we don't have perfect knowledge of how Ada talks, and instead we are using our own average protocol for average source, then we shouldn't expect PI and QI to be the same, and nor should we expect the AI basis and BI basis to be the same. So how do we do this? So to do this, we actually use the idea of the variational length coding. And in the quantum case, we also call it the indeterminate length coding. So let's say if we treat QIs as classical distribution, then we can assign code word CI with length Li equals to log 1 over Qi. And by doing so, we can construct each unit of computational basis I by assigning the first Li available qubits to Ci. And then all we need to do is to map our original row 0 to this computational basis. And doing so only requires a unitary evolution. And in this new basis, we will have this new row. So the expectation length of a single code word will actually be exactly the quantum cross entropy. So you may say, okay, great, now we are done. But we also have to prove this protocol works perfectly, meaning that it can do lossless data compression. By saying lossless data compression, it means if I go through this protocol, in the end, the fidelity of this protocol will be approaching 1 in certain limits, for example, large N. Otherwise, when I do the compression, I lose most of my data, then that's not good. That's not real successful quantum data compression. So to deal with this, we use the classical language of having a large N copies. And in this case, we will have basically big N copies of source state. And it can be written down quite complicatedly, but these are just details, and we will just quickly go through it. So here, the idea of the proof is basically using the idea of typicality. And we can define a projector onto a length condition. And this length condition basically says that on average, I need the number of quantum cross entropy of qubits to successfully contain all the data. Let's say intuitively, I might have a long strip of qubits. And what I do is to transform all the quantum information that I want to compress towards the front end of that strip. And then I can do a projection just onto the length of n times s rho 0 sigma 0. So basically, only the front end of the qubits will be needed to transmit to the other end, let's say where Bob sits. And I can just discard the remaining qubits. By doing so, I will only need to transmit number of qubits that are much smaller than the original information bearing qubits. That's why the compression can work. So a sanity check will be that doing so can transmit our information faithfully. So by doing some math, we can show that the fidelity actually approaches 1 in the when n goes to infinity. So this is very commonly used in any discussion on data compression, which means if I'm sending a large amount of information, then on average, this protocol works. So now we have briefly talked about the idea of quantum cross entropy and what it means in the context of data compression. We are jumping into something more interesting and more closely related to machine learning, which is that I'm going to talk a bit about maximum likelihood principle, and then talk about the relation between cross entropy and likelihood. So let's first start a short quiz. Let's say Cindy is a naughty girl, and she tossed the coin for 200 times. And actually, every time she gets head. So she turns to David, saying, I'm going to toss a coin for the 201st time. Do you think I will get a head or a tail? So if David is some stubborn guy and have been very booky in his probability training, he might say, well, regardless of your previous results, it's always 1/2 probability of getting head and 1/2 probability of getting tail. So you will have equal probability in getting head or tail. Well, if that's David says so, then he has overlooked one fact, which is if it's really equally likely to have head or tail, then how likely it is to have a head for 200 times consecutively. You know that it's very unlikely, and so when you observe 200 times of heads in a row, you might start wondering, is this really a fair coin? So probably this is not even a fair coin, and how do we model this? So the assumption is that each coin toss is identical and independent. And now we can say, well, let's say the probability of getting H is theta. This is our model parameter. And now let's think, based on our data, what is the most likely value of theta? If it's 1/2, if theta is equal to 1/2, then we will say this is a fair coin. But if theta is not equal to 1/2, then it's not a fair coin. So the data we have is x1, x2 to xn, where each xi is either head or tail. So now the problem is, well, given the data set we observed, how likely, given the data set we just observed, how likely is it to have a theta is equal to 1/2, and how likely is it to be 1, etc. So let's say we define the likelihood to be the probability of getting a certain data set as a function of parameter theta. And the maximum likelihood principle tells you to take the theta that maximizes this likelihood function. So this argmax tells you to take the theta that maximizes either this large L theta or little L theta, since they only differ by the log function. So it doesn't really change the behavior of when you reach the maximum or minimum. So from the context of our coin problem, it's finding the theta that make it the most likely to observe the data, which is what Cindy tossed. And since we only get head, and to maximize that probability of getting 200 heads in a row, actually, we will need to take theta to be equal to 1, which means that the coin is completely biased, that it can only generate head and cannot generate tail. And this is based on the data we observed. And so if I were David, I would say, well, the 201st time you toss the coin, I would bet that will be a head again. So this is the idea of maximum likelihood principle, and it's widely used when designing machine learning algorithms, from the simplest ones like logistic regression or other regression models that help you predict the housing prices, to the more complicated ones like those image classifications using neural networks. Now that we have talked about maximum likelihood principle, we are going to talk about its relation to cross entropy. So in the classical case, it can be summarized into two sentences, which is classical cross entropy is equal to negative log likelihood. And maximizing likelihood is equivalent to minimizing classical cross entropy. The second one is actually a corollary of the first one, even though the second one is more useful in the context of machine learning, because when we use the principle of maximizing likelihood, it also means we need to define a cost function that is equal to the classical cross entropy. So we just need to minimize that cost function. These two ways are both very widely used and are usually equivalent, but there are also special cases that cross entropy is more widely used, that we just try to minimize the cross entropy, and sometimes in that case, maximum likelihood principle doesn't really apply. So now let's give a short proof of why this is the case. As usual, we are going to define probability distribution based on model parameter theta. And we also need an empirical data distribution that is based on the data we observed. And here, this is like a delta function in physics. Just when x is equal to xi, it is equal to 1. And when x is not equal to xi, it gives you 0. So this is an indicator function. So classical cross entropy can be proved in this fashion, that it's equal to the negative log likelihood. And because of that, minimizing this term is equivalent to maximizing this term. And now we jump into the case when we have the quantum case. So we have this quantum cross entropy, and we also have this maximum likelihood principle, which can also be used when we do some quantum measurements and we have some data based on that output, and we can also construct a likelihood function. So in the more ideal case, where we have perfect quantum data and the quantum state rho has not been measured or approximated, then minimizing quantum cross entropy is exactly the same as maximizing likelihood. And a detailed proof is provided in the February paper. And here it shows you a rough idea of why it works. Basically, if we want to minimize the quantum cross entropy, then it is actually the same as minimize the relative entropy here. And we know to have this term to be minimized, we basically want rho is equal to sigma. And again, it can be proved that in the special case we are considering here, maximizing log likelihood is actually the same as giving you a perfect knowledge of the original quantum state rho. So because these two terms are the same, we conclude that when we have perfect quantum data, then minimizing the quantum cross entropy is the same as maximizing the likelihood. However, this is not always the case, because usually when we do something quantum, it's inevitable to make some measurements. And when the measurements come in, we will have the wave functions collapse and we will lose some information. And because of that, something that is beautifully held in the classical case will break down. So let's look at it from another perspective of generating quantum data. Let's say, how do we consider the data generation process in the classical case? It means we make many independent and identical classical measurements. A simple example would be tossing a coin. So every time we toss a coin, we either get head or we get tail, which means we make many measurements, and the outcome can be head or tail, and we can represent them as bits. It's either 1 or 0. And in the quantum case, it becomes make many independent quantum measurements on identical copies of rho. And of course, we can do different sets of measurements, like considering different directions. And one way to describe these quantum measurements would be by a complete set of projectors. And then the observable can be defined as this. And of course, if we want to do tomography or something similar, when we make quantum measurements, we definitely want to have different sets of projectors so that we can get more information of the original state rho. And now, if we already generated these measurement outcome, how do we incorporate it with quantum cross entropy? Well, just like in the classical case, we constructed empirical data distribution. Here, we also construct empirical density matrices. Let me tell you a little bit about how to interpret these weird constructions. So this rho O represents the operator perspective, which means, let's say when I generate the classical measurement to the quantum measurement, how do I understand it? Let's say if I toss a coin, I either get 1 or I get 0, and I can say, well, actually, seeing these results represent what kind of projector I use. It can be a projector that gives me the head, or it can be a projector that gives me a tail. So what really matters in the measurement is what projector I use. And if I consider it in this way, then all I need to consider is what the projector that I used, which is corresponding to the measurement outcome. Another way is called the state perspective. And how do I understand that? Here, note that sigma is just a model parameter. And when I look at tossing the coin problem, when I see a hat, I will say, well, this hat is just the state after making the measurement, which is tossing the coin. And in the quantum context, it will be, well, let's say if I have this model parameter sigma that I'm going to vary and see what it is. Let's say if I have sigma and I have observed this measurement output and it's corresponding to the pi n, which is the operator, then this pi n sigma pi n is basically representing the state after the measurement. And that's what really matters in understand what's going on. So basically, these rho O and rho S tells you two different perspectives in understanding these measurement results. And note if our density matrix is of rank 1, then these two perspectives will coincide. And now I can calculate quantum cross entropy in both perspectives. And interestingly, even though the constructions are a little bit different, they are both lower bounded by the negative average log likelihood. So this shows us that regardless of which perspective we are using, this lower bound has told us something on what quantum measurements have done for our likelihood function, for understanding between quantum cross entropy and the likelihood function. And note that in the classical case, it will become an equal sign instead of this unequal sign, which tells us that in the classical case, we make measurements and we still have the perfect knowledge of the original system. But in the quantum case, when we make some measurements, we will have some information loss. And due to this information loss, the equality becomes inequality. And of course, there needs to be further work done on why it is exactly like this and what kind of information is lost and how do we estimate the difference between these two terms. And of course, there is a takeaway message of this simple construction. Of course, it tells us that the quantum case is different from the classical one, and the difference basically comes from the information loss when making measurements. But this also tells us that if we really want to do full quantum machine learning, which means we have quantum data coming in and we go through everything in the quantum computer using quantum algorithms, and we get quantum predictions out and everything is quantum. And maybe only when we want to get a classical prediction, we make some measurements. If we really want to do this perfectly, we should actually delay all the measurements towards the end. Why do we have to do that? Because if we make quantum measurements here and there in the middle, then some nice rules that are widely used in machine learning will break down, and that definitely is not something we want to see. So this suggests that it will be really great if we can delay all the measurements towards the end until the very last step that we want to do some test or predictions, so that we make some measurements and get, say, a classical output function if that's what people want. And to do this, it's actually perfectly possible because we have this result in quantum circuit study, which is called the deferred measurement principle. So we can actually replace every control NOT gate so that every quantum measurement can be delayed till the very end of a quantum circuit without changing the output. So this is the takeaway message of the result. Basically, if we want to do perfect quantum machine learning that has good performances, no weird biases, and no all those weird barren plateau problems that are talked in a lot of quantum machine learning papers, then we really need to utilize the deferred measurement principle so that we can delay all the measurements and avoid all those weird occurring problems due to measurements. So of course, this work is still at very early stage of a theoretical understanding of quantum machine learning and also its impact on many fields. So of course, one thing that is on my wish list is to find gravitational interpretations of quantum cross entropy. Because as we've seen that quantum relative entropy has played an important role in the development of quantum gravity. And there are a lot of interesting results. And quantum cross entropy has its unique advantage compared with quantum relative entropy. One thing is that it's easier to calculate because it's only the second term. And if we can find some gravitational interpretations, we can probably really achieve the goal of putting quantum gravity in the lab, because all these quantum cross entropy thing is so useful when we think about doing quantum machine learning on a quantum computer. And if we can really put a black hole or simulate a black hole on a quantum computer, we definitely want to have a better understanding of quantum cross entropy so that maybe our machine can just learn a gravitational system automatically, and we can say goodbye to all the nasty calculations that now have to be done by hand. And another thing will be to use a quantum cross entropy to study the time evolution of quantum many-body systems, because this term essentially tells you some differences between some original state and some other states that you can say, or either say it as a reference state or some state that can be tuned by your own parameters. And it will be interesting to see how this quantity can be useful in studying quantum dynamics. And of course, just as classical cross entropy has played a central role in classical machine learning, of course, it will be great to find a lot of applications of quantum cross entropy in quantum machine learning algorithms, and preferably to demonstrate quantum supremacy in doing quantum machine learning. of course, we've had a lot of quantum algorithms that demonstrate quantum supremacy, for example, the Grover's search algorithms, and they are also supervised and unsupervised learning algorithm in quantum machine learning that has less time complexity. And I have an ongoing work on quantum semi-supervised learning that also shows some quantum algorithms that has quantum supremacy in the context of time complexity. But it would be really awesome to see that quantum cross entropy is actually a superior term in studying quantum machine learning, because now a lot of quantum machine learning algorithms or learning algorithm for quantum tomography still uses classical cross entropy or the classical KL divergence to as a cost function to do the learning process. And it will be great to show that quantum cross entropy is actually a more suitable term in the context of training, since we are dealing with a quantum system and trying to learn a quantum system better. Of course, it will be more efficient if all the concepts and algorithms are also quantum compared to like try to fit it into a classical box. So these are the outlook I have, and of course there are a lot of things to be done in quantum machine learning, and hopefully the advantage of quantum machine learning can also be used in understanding gravitational systems and quantum many-body systems better. So thanks for listening, and here is the outline of the talk, and I would be happy to answer any questions either in Mandarin or in English.
Oh, thank you very much. So, do people have questions? I have some questions, but I'll ask after everyone else and after the recording is stopped. Because
Sure.
I have some very very basic and naive questions, but I wait for other questions first. Oh, no questions. If there are no
Sorry,
other,
may I ask a
yes, please.
Sorry, may I ask a question?
Please do.
Yes. So I want to ask about the point you said about the density matrix will collapse after your measurement. So because of this kind of property, it seems to me that it would be great to have a one-shot version of this quantum cross entropy. And do you think it's possible to construct a one-shot version of this kind of quantity, or do you have any comments on that?
So if you take n to be equal to 1, then that will be the one-shot case, right?
Yeah.
So because this n can take any value, so even if you do it in a one-shot, this inequality still holds. So that's like a simple answer for your question. But of course, actually, this inequality can also be proved if we use some knowledges in the one-shot quantum information theory, like all those sandwiched relative entropy. If we actually use knowledge on that, we can also prove this lower bound. So in the paper, the proof was not based on any like was purely mathematical, but actually if you've studied one-shot quantum information theory, you can also derive this inequality using resulting that. So I would say like these constructions are actually very closely related to the one-shot quantum information theory.
I see, that makes sense. Thanks a lot.
Oh, but just following that question, does one-shot measurements have any advantage over the case where n is greater than 1 though?
So if just mathematically looking at this this inequality, it holds for any n, but
right.
of course But of course, in reality, if we want to have a better knowledge of the system, of course, we would like to have n larger. But interestingly, actually, if we really want to use these rho and these results to understand the system better, actually making n very large wouldn't help a lot. It's like you have a moderate n, you have a smart chosen set of measurement operators. It actually matters more than if you have a large number of very large number of measurements.
I see. I see. So there's some optimization in n and these projectors pi.
Yeah.
I see. Are there any other questions? Okay. If there aren't other questions, then we'll thank the speaker again. Then I'll stop the recording. Okay, thank you very much. It's a very clear talk.